That's just acknowledging those people. So what's RS Ophiuchi? It's something called the recurrent nova. It brightens suddenly. So if we just see, for example, this this picture in the top right there shows you a before and after shot from its outburst, its last outburst in 2006. So you'll see it is actually just about visible there in a deep exposure, but it becomes much brighter. So for anybody who knows about magnitudes in astronomy, then it goes from about 11th magnitude, which is a lot fainter than the naked eye can see, to about 4th or 5th magnitude, which means it becomes just about visible to the unaided eye. And we've seen this happen. We've seen this brightening happen a number of times over the years. In 2006, 1985, 1967, and so on, back to 1898, which is when it was first noticed. The current outburst, the one that's happening at the moment, was discovered by someone called Keith Geary, who's an amateur astronomer in Ireland, and he was just scanning the skies with binoculars, and he happened to notice that it was bright. And so he told everybody via the internet, and we all found out sort of overnight that night. So he found it on August the 8th at 20 past 10 universal time, so 20 past 11 in the evening British summertime, and let everybody know. And this is the brightness. So this is the AABSO, which is the American Association of Variable Star Observers, and lots of amateur astronomers around the world submit their observations to this group, and they put them on the web, and you can grab things like this light curve. So this is time along the bottom, brightness along the horizontal axis and magnitudes, and you'll see that it burbles around at about 11, and then all of a sudden, wham, it's suddenly a lot brighter. 1, 2, 3, 4, 5, 6 magnitudes brighter, which is more than 100 times brighter, and then it's fading away. And this goes from, this is August the 8th, and here this is the 10th of October. That particular graph. You'll also see at the bottom there, I just mentioned that it was also detected about the same time as a gamma ray source by a satellite called Fermi. But Keith was excited enough to be the first person in the world to notice it, as far as we're aware. So what are these things? What are novae? I don't know how I get rid of that thing. I'm afraid. Never mind. So novae are binary star systems, which are in general in novae you have a white dwarf. So the white dwarf is here in this artist's impression, and then there's a companion star, which is either a main sequence star or a red giant. In the case of RS Ophiuchi, it's a red giant star. So if you think about what's a white dwarf is something that's the end state of the evolution of a star like the sun. So this is just a graph showing you sort of time goes downwards, and on the horizontal axis, it's got the mass of the star in units of the sun's mass. So you start on the main sequence when you convert in hydrogen to helium, and then as the star evolves, it goes through these various phases, and then this is the end point. So for stars up to about 8 or so solar masses, the end point is a white dwarf, and it goes through a phase where it becomes a red giant, it evolves to become a red giant. Eventually, the outer layers are lost to become something called planetary nebula, a cloud of gas and dust that's illuminated by a hot white dwarf at the middle. And there's a nice picture of one here. That's a nice planetary nebula with white dwarf visible as the bright spot in the middle. So white dwarf's about the size of the Earth, but about the mass of the sun, roughly. And in the case of RS Ophiuchi, it's probably about almost 1.5 times the mass of the sun. So it's a very dense object. It's where all the nuclear reactions used to take place. but they've stopped by this point. But it's still, because it was the core of the star, it's extremely hot initially, and it takes millions, if not billions, of years to gradually cool down. So what happens in this binary system is that you get accretion, material falls from the companion star onto the white dwarf, and that's sort of illustrated here with this sort of stream of material coming across. And as it accretes onto the white dwarf, it sort of builds up. So mostly hydrogen, so you get this accreted layer of material building up. And imagine the sort of picture, if the Earth was a white dwarf, we'd be standing here on the surface of the white dwarf. It'd be quite hot, and gravity would be quite high, but that's all that for the moment. But imagine us standing on the surface of the white dwarf. A large part of the sky would be filled with this red giant star, all right, because it's quite relatively close by, big red giant star, and hydrogen's falling in on you from the red giant, building up on the surface of the white dwarf. As that stuff builds up, the weight of it is obviously increasing, so the pressure at the base of this material that's being accreted from the companion increases, the temperature increases, the density increases, and at some point you get to a stage where you start nuclear reactions in that material. So you start converting the hydrogen into helium, just like you do in the core of the sun. Except the difference is that in this case, this material is not like a normal ideal gas, where if you were to start nuclear reactions, that releases energy, and then that energy heats the gas, and then the gas expands. And when a gas expands, it cools down. So there's actually a natural safety valve. So as it starts to put energy into nuclear reactions and heats up, it expands. That takes the temperature down, which lowers the rate of nuclear reactions. So it sort of keeps it under control. In this case, it's what's called a degenerate gas. And in a degenerate gas, there isn't a link between the temperature and the volume effectively. So the temperature goes up when the energy gets put in. Instead of it expanding, it doesn't expand, so it can't cool. So the temperature goes up. As the temperature goes up, that increases the rate of nuclear reactions, which makes the temperature go up even more as a really high power temperature. And so actually what that results in is an explosion. So it's a thermonuclear explosion, called a thermonuclear runaway. It's a bit like, and I don't recommend this, the white dwarfs the size of the Earth, covering the whole of the surface of the Earth with hydrogen bombs, thermonuclear bombs, and setting them all off, which would be a bad idea, generally. But in this case, that's what leads this thing to become so bright so suddenly, as this triggers this explosion. And as we'll see in that explosion, stuff gets chucked out. But what it doesn't do, in the case of Novae, is destroy the white dwarf. So the explosion occurs on the surface and stuff gets chucked out. So the white dwarf lives to fight another day. And once all the outbursts gone on, this whole accretion process can start again. And so the layer builds up again. And sometime later, and that time varies from one object to another. In the case of RS Ophiuchi, I said there was an explosion in 2021, so just a few months ago. The one before that was 2006. The one before that was 1985. So it takes it roughly 20 years or something before conditions are right for another explosion. Now, in the end, in some novae, it might be thousands of years before the next explosion. In what we call recurrent novae, the time scale is just short enough that we've seen more than one explosion. So we call them recurrent novae. All novae we think recur, but some of them on such long time scales we've only ever seen one explosion. And it's all to do with how much material is coming across from the other star, how massive the white dwarf is. That's what affects the time scale before the next explosion. It might be that as a result of this process, we think that if you gather all this stuff, comes across, falls into you, bang, it goes off. Some of it's certainly chucked out into space. If some of it remains on the white dwarf, that means after every period, the white dwarf is getting a bit more massive. And we know that there's a limit on the mass of the white dwarf. It's called the Chandrasekhar mass, which is about 1.4 solar masses. And we think if you get to that stage, then basically the white dwarf will explode as what we call a type 1a supernova. So it's one way to get these type 1a supernovas is in these sort of systems we think. And we think the ones that we see explode relatively often, like RS Ophiuchi, have probably got white dwarfs that are close to this limit. I doubt we'll see what RS Ophiuchi explode as a Type 1a supernova in our lifetime, sadly. But let's see. Be interesting if it did. So what's happening? Materials ejected from the white dwarf. The speed at which it's ejected as a result of this explosion is pretty big, hundreds to thousands of kilometers per second. And I've just sort of converted that into numbers that we're more used to. If you like, miles per hour, about 2 million miles per hour is a pretty fast speed. In other words, if it was chucked out from the Earth, it would get to the moon in about 6 minutes. It would take it about 42 hours to get from the Earth to the sun. But it's pretty fast, 2 million miles an hour. And then if you imagine it sort of being chucked out, and you imagine this thing off in distant space, initially when you look at these things, you're only going to see a dot, because it's so far away you can't see this expanding stuff. But eventually the stuff's going to expand out to be big enough that when you take a picture with a telescope or something, you might see the actual material that's expanding. And you can sort of work out how long that will take. And if you know anything about sort of using a telescope or something from the ground, you might know that atmospheric blurring tends to blur things to have a sort of angular diameter of about an arcsecond, so 1/3600th of a degree. And if I sort of say, okay, let's imagine a nova which is about 1,000 parsecs away, so about 3,000 light years away. Let's imagine it's got an ejection speed of 1,000 kilometers per second. I can just work out how long it takes for something expanding at 1,000 kilometers per second to get that big. And it's about 2.5 years. So after an explosion, you wouldn't expect to be able from the ground to see the expanding stuff for about 2.5 years. Here's some pictures I took earlier. So these are visible light pictures coming off the right-hand side of the screen, slightly annoyingly. We'll just have to live with it at this stage, which show you the negatives. So, you know, where it's black, it's actually bright, but it shows you these large expanding nova shells from some novae that we did a survey of some years ago. So these are actually all quite old novae. I think H.I. Dell exploded in 1967, GKPO was 1901, 1934, and so on. So they've grown big enough to be able to take reasonable photographs of the material. I'm hoping nothing important goes off the right-hand side. Okay, so what happens in these things? What you also get is you get shock waves. So you chuck this stuff out at really high speed. And in the case of RS Ophiuchi, because there's a red giant star as a companion, red giant stars have a stellar wind. So they have a wind of material that expands outwards from the red giant, a relatively dense wind. And so when this stuff's kicked out at 1,000 kilometers per second, it runs into the red giant wind, which is only moving at about maybe 20 kilometers a second. And so it smashes into it. And if something smashes into it at supersonic speeds, which it would be if it's 1,000 kilometers per second, then you get a shock wave. So in a shock wave, basically it's the same thing as like when a supersonic aircraft is moving through the air, through the atmosphere. It's moving faster than the speed of sound. So any atmosphere out here can't possibly know the aircraft is coming until it arrives. Because the only way it could get out of the way is if there's a system of sound waves ahead of the aircraft that sort of pushes it out of the way. All right, so it's just sort of sitting there going, lively sitting there, and then suddenly this aircraft comes smacking into it, and that's what's a shock wave. It gets a shock. It's surprised. And in a shock wave, the gas is compressed, and it gets heated, in fact, to temperatures of millions of degrees. And if you happen to do the physics of gas dynamics or shocks or things, you might end up deriving these things. But basically, this is the temperature of the gas behind the shock. For a shock of speed 1,000 kilometers per second, then the temperature would be about 10 million degrees. So it's very hot. Any gas at temperature of millions of degrees emits X-rays. And you can remember, if any of you have done things like black bodies, then you might know about Wheaton's law. So Wien's law tells you there's a relationship between the peak of the black body spectrum, the wavelength at which that peak occurs, and the temperature of the black body, which is given by this. Or if you want to turn wavelength into energy, you can do E equals HU, which is E equals HC over lambda, and you can get an equivalent thing that tells you that the energy of the peak of the black body is given by this formula. So I just have to put the temperature of 10 to the 7 or something in there, and I'd end up with 4,000 electron volts, 4 kilo electron volts. For anybody who's familiar with those things, that's an X-ray energy. So it's worth looking at these things with X-rays, which is what we do. X-rays get absorbed by the atmosphere from outer space. So any X-ray telescopes we use have to be on spacecraft. So we use an X-ray telescope called SWIFT quite commonly for our NOVA observations. So here's an artist's impression of SWIFT. I thought I'd show you a real picture of SWIFT because it's got real people. So you can see what the size of it is and everything else before it was launched. It's basically designed to detect gamma ray bursts or gamma ray explosions. But in between looking at gamma ray bursts, it quite often spends a lot of time looking at our novae. So there's a big team of people that have been observing this, and they're based in Leicester. The University of Leicester runs the SWIFT. I really don't know why I'm not, my thing's not filling the screen slightly annoyingly. Never mind, I'm just missing the right hand edge. So what are we showing here? So Kim Page at Leicester produced this plot for us. And there's a big team of people around the world who are on the big email list where we all share these dates and discuss what's going on. So let me explain to you what the X-ray observations of this 2021 explosion of RS Ophiuchi look like. 2 graphs here. Look at the top one first of all. The top one is showing you basically the X-ray brightness against time. And this is days since the optical peak, which was the time at which the visible light reached its brightest, which was about the 9th of August, so roughly lunchtime. So that's what these days are here, 20, 40, 60, 80 days. And what you'll see is the X-ray brightness. It's on a log scale, and you'll see it brightens quite rapidly, and then it sort of goes into this decline, and then it goes into this sort of weird brighter region again, where it sort of flails about, you know, seemingly quite randomly, reaches a high point and then starts to decay again, and now you see it's on decay. A bit sadly for RS Ophiuchi. Anybody know about astrology? So astrology, which we probably banned in this department, astrology, you know, the signs of the zodiac. There's 12 signs of the zodiac, like Pisces and Aries and these constellations. So the sun, that's the path of the sun across the sky. So as the Earth goes around the sun, and you look from the Earth here, past the sun, in the distance there's a constellation. And as you go round and round, there's a big set of constellations that go around the circle. They're the 12 signs of the zodiac. In fact, there's a 13th sign of the zodiac, which is Ophiuchi, which is the constellation that this star is in. The astrologers couldn't get that right, I don't know why. The sun spends more time in Ophiuchi than it does in Scorpius, if you're a Scorpio. Anyway, so what that means is that Ophiuchi goes behind the sun. Sadly, Ophiuchi has gone behind the sun about a week ago, or yeah, the end of last week, I think it was. That means we can't point in our X-ray. The X-ray telescope is probably not quite behind it yet. We're not allowed to point the X-ray telescope near the sun because it would burn it out. So it got to the limit. So that's the last set of data we're going to get until, I don't know, sometime in the new year. So we're going to miss out on the last bit of what's going on here. Okay, that's one thing. What about the bottom bit? The bottom bit is showing you something called, if you could read this, you might notice that says HR, hardness ratio. What's a hardness ratio? It's the ratio of the brightness in a high energy part of the spectrum to a low energy part of the spectrum. So it's telling you something about the slope of the spectrum. If the more high energy X-rays, this is less high energy, more low energy, in which case the hardness ratio would be low. if it was like this and there was more high energy X-rays compared to low energy, the hardness ratio would be higher. So what you see is quite a high hardness ratio that gradually declines. And then when this weird burbly thing that gets brighter happens up there, this dips down. And now you see it actually starting to come back up again. So what's actually going on with this X-ray, we believe, is that what you see, this bit that you see here, is the shock wave. So when the shock wave is going out and you produce this 10 million degree gas, it's very hot, so you get more high energy X-rays. And so you see this quite high hardness ratio. And it expands out, the shock wave gradually slows down, so it's expanding out as it sweeps up material. And so the temperature slowly goes down. And that's why this thing happens. This thing is a completely different part of the system. There's a shock wave expanding out, but in the middle is this very hot white dwarf. And on the hot white dwarf, it's still sort of using up the hydrogen fuel, burning away what's left of the hydrogen that it attracted. There's a big explosion, but then there's stuff left there that has to be burnt away. And so what happens is this thing expands. Initially, all you can see is the outer stuff. But as it expands out, this becomes more transparent, and you can see through it, and you start to see the white dwarf itself. So this is the white dwarf becoming visible. And the white dwarf isn't as hot, and so the hardness ratio goes down. We think that's a pretty consistent explanation of what's going on. We don't understand, really don't quite understand the details of why it varies so wildly yet. We have some ideas, but none of them really work brilliantly. We discovered that phenomenon in 2006, actually, with Swift. So that basic picture we discovered for the first time in 2006. And this just shows you the same plot, but now it's got the current observations. There's a log scale on the time axis as well, so it looks a bit different. But the current observations are red, and then the last of the 2006 observations are in grey. And you can see there's the same sort of behaviour, although it is different this time. And again, we don't yet understand the differences. So I apologise for not understanding everything, but people don't understand everything, right? And this is all quite new. So that's X-rays. So we're very keen on X-rays. We like X-rays. What about radio? So Jodrell's famous for its radio observations. So I'll show you some radio observations made with these telescopes. So we've been using the Merlin telescopes, which is 6 or 7 radio telescopes, depending on whether we use the big one in the middle, the Hubble telescope. Spread across the UK, connected by optical fibre. They give us quite a zoomed-in view, sharp view. This is a telescope at Oxford called Amy, the Arc Minute Imager, large array. And then there's Meerkat in South Africa. There's the very large array in the USA. And there's LOFAR, the low frequency array in the Netherlands. So what does the radio show? This is the radio brightness against time. And I've just put basically all these data are on that graph. So I tried to give them different colors so you can disentangle them. But they're all these are all made at different radio frequencies. So the measurements of the brightness in different bits of the radio spectrum, and each instrument is designed to work in different bits of the spectrum. But what you see basically is you see this sort of very, not immediately zero. This is when the optical peak was, remember, middle of the day on August 9th. So it doesn't rise immediately. It's a bit delayed by a few days. But because we sort of like wanted, one of the great things about recurrent novae is they have exploded before. And so you can do a lot of work on it, but things happen rapidly and then it goes away. And if you don't get yourself organized, that's it, hard luck. You've missed observing it, but at least you can wait 20 years and observe it again. So I did my PhD here on the 7th floor starting my PhD in 1985. And RS exploded in January 1985, so that was the subject of my PhD between 1985 and 88, if that tells you how old I am, was the 1985 outburst. And we developed models and we did observations to a certain level. And then in 2006, it explodes again. And by that time, we've got much better technology. We've got some better idea of what's going on from what we did before, so we can do a better job of it. And 2021, here we go again, the third outburst of RS Ophiuchi I've been able to study, and each time we're learning more about what's going on. So we were ready to start observing it very soon. So we started observing straight away, which was not the case in 1985. And in 2006, I'll show you in a minute, we did get some early observations, but we got much better ones this time. But basically it sort of rises and then roughly sort of turns over and starts to fall. What can you do with that? You can do things like this. Looks complicated, I apologize. These are spectra. So this is the frequency in the radio spectrum. This is the brightness. And so in this case, each colored set of data are different times. So the red one is 2 days after the optical peak, 3 days after, 5 days after. So it generally sees the brightness is going up. But what we're also interested in here is the slopes of these spectra. And you'll see the slopes change at different times and in different parts of the spectrum. And that's what gives us a clue as to what's producing the radio waves, what physical mechanism is going on that's producing this radio emission. So it's not just brightness, it's the spectral shape, a bit like it was for the X-rays, where we looked at the hardness ratio, high energy to low energy X-rays. So in fact, if you're interested, these numbers are basically just the flux, the brightness, proportional to the frequency to some power alpha. So these are the values of alpha that I've just labeled the thing with. Okay, and then just to show you, probably show you this one. So this one is the particular bit of the spectrum, and this is just a comparison between the current outburst and the previous outburst that we had data for. So if you just look at, for example, the current outburst within Merlin for the solid green dots, and then ignore the blue stuff for a minute. You can just about see underneath, there's also last time round, 2006, the dotted line with plus symbols is this one that goes in underneath here. And you might be able to tell what we had. These are observations from 2006, and this was like a real surprise. So I knew RS Ophiuchi had exploded, but in 1985, this is what we saw. So we saw this rise here. But if you know the explosion happens here, then you'd sort of not really think you're going to see much if you observe it here, because it's sort of fading away. It's getting. You'd imagine it's probably doing this. You're probably not going to see anything. I was a bit naughty. I went down the corridor to the bank and asked the person scheduling the telescope, "Can we observe RS Ophiuchi?" And I sort of knew that I wasn't really convinced we were going to see anything. And we actually saw it, and we saw it getting really. We did 2 observations, and we saw it going brighter and brighter in each observation. So that was a real sort of surprise, actually. There was this very early, rapid rise. And so one of the aims this time around was to observe that rapid rise, to check it really happened, apart from anything else. We only had one look at it before. Did it happen again this time? And indeed it does. And now we've got observations of more than one wavelength. And so that should help us try and understand where that comes from. As we've seen in a minute, it's not something we really completely understand. So I'm just going to flick through some of these things. This is sort of interesting. If you're trying to understand what these things mean, you normally start with spherical symmetry. Anybody heard of the spherical cow, the famous physics spherical cow? Imagine a spherical cow. Obviously, we know that cows aren't spherical. One of the very simple things actually involves a cubic cow for understanding what goes on. But we can do models of what we should expect for the radio emission that I won't go into. But basically, they rely on thermal emission. So a hot gas, we know there's a hot gas, you can see it in the X-rays. We know there's probably going to be shock waves, see that stuff's expanding at high speed. So you can work out what a hot gas should produce in radio waves. And it just comes from particles like an electron flying past an ion just imagine it's hydrogen, so electron flying past the proton gets accelerated as it goes past, and that produces radio waves. It's something called Bremsstrahlung. So basically, we can work all these things out under that assumption, and we can do, we can make it. We can put in things like how much mass is ejected, what speeds it ejected at, and so on, and we can fit that to the observations. And people have been doing that with Novae for decades. Basically, this is the first time it was done was back in the late 1960s, early 1970s. But these models don't work. They certainly don't always work. In fact, it looks like how they are in reality. And they don't do things like they don't produce this steep rise. So these simple ones don't produce the steep rise. They also don't give you the spectra that we're seeing here. In a simple model, you should either get the index, these numbers in here, either 2 when it's all small, as it starts to expand, it's very dense and therefore it's like a black body, or it should, as it expands out and becomes transparent, it should go to being roughly flat. So an index of just minus 0.1, roughly flat. And we see different values of the indices in here, where we see steep and negative values and see different values of the positive index. The other possibility, and it's almost certainly going on, is that you've got synchrotron radiation. So synchrotron radiation comes from relativistic particles, so particles accelerate nearly the speed of light in shock waves, and in the presence of a magnetic field, they produce synchrotron radiation, and that gives you different indices in these spectra. And so it looks like in something like RS Ophiuchi, we've got a mix of the hot gas, the thermal emission, and this relativistic particle emission, but it's quite complicated. And what's important to say is it's neither cubic, spherical, or it's ellipsoidal, as we'll just have a quick look at to finish. So you probably know that with radio images, you might know that when you take an image of something, anything, your eye, whatever, you get diffraction effects that reduce the sharpness of your view. And the sharpness of view is actually dependent on the wavelength you're working at and the diameter of the aperture you're collecting the light with. And it's just a ratio of those two things. So if you want to get a sharper view, you need this angle to be small. So you either need the wavelength to be short or the diameter to be big, and that will give you a sharp view. The problem with radio waves is that the wavelength is very long, and there's nothing we can do about that. And so you need a very big diameter to be able to see something with a sharp view. And the problem is, how do you make a huge telescope? You can't make them much bigger than the Lovell telescope at Jodrell. So that's why we use something like E. Merlin. So we have multiple telescopes that spread across 200 kilometers in the UK, and we connect them together with an optical fiber system. So that we effectively synthesize the sharpness of view we get from a telescope that big. And we don't make a telescope that big because that would annoy everybody in Birmingham. Very dark. Right, and of course we can go even bigger than that as well. We can go out to intercontinental baselines. We do that regularly in something called very long baseline interferometry, where we join forces with other colleagues in other countries around the world. And we can make telescopes the size of the planet, and that lets us really zoom in. So here's some RS Oph observations. I just grabbed, this is the observation that was made on the 16th of October, a few weeks ago. So this is just where the object is in the sky, some calibrators, and this is RS Oph. RS Oph is quite low down in the south, so it never gets to more than about 20 to 30 degrees above the horizon, so relatively low down. And this is time, so this is about 2 o'clock in the afternoon to about 8:30, 9 p.m. So that's our observation. If you know anything about these sorts of things, you might recognize what these diagrams are. Basically, that big picture of the Lovell telescope I said that we'd like to build, that would annoy everybody in Birmingham. In reality, we've only got 7 bits of that big telescope, right? Which are the 7 actual telescopes we use. So it's a bit like getting a pair of binoculars or a telescope and putting tape over the end of it and blocking it all out apart from 7 little pinpricks that let the light in. That's what it is. And so you get quite a distorted image by doing that, you might imagine. And then this is effectively how the object sees the telescopes. So as the telescope sort of moves across the sky, this is what sweeps out. There's that little dot, the pinprick in the masking tape on the end of your thing. That dot sort of sweeps into a line. And then for each pair of telescopes, you get sort of pairs of these lines. That's the inverse of that one there. And also we can get to be quite thick because we can use different frequencies, and we can what you're after is something that was really like this to be completely full, and then you get the best quality image. We've only got 7 telescopes, and often 6 or 5 of them, and so there's lots of holes in here, which makes it hard to analyze the data. This is what the pictures end up looking like. This was our first image of RS Oph. So false colour, so the brightness just relates to the colour, so you can see white is the brightest in the middle, and this is just like a patch of sky. And one thing that's important is this little line going around here, because this is what's called the beam of the telescope, and it means that if the actual object we're looking at was a dot, because remember these things are very far away, and so if it's only a dot, you'd have expected to see a dot. In fact, the dot gets blurred out with this shape, and it does that because of partly where it is low down in the south, ends up sort of extending it like this. So that shape tells me that actually it's just a dot. It's unresolved. Okay, it's a point source. A little bit later, can't read when that is because the time's at the top up there. I don't know whether this moves around, does it? Oh yeah, there we go. So that's August 27th. That's 18 days after the explosion. Now maybe you can see that things are changing a bit. Look at the lump on the left-hand side. Right, there's something happening that it's sort of becoming lumpy on the left-hand side. And I'll just flash through. That's September the 1st this year, September the 6th. September the 18th, October the 4th, October the 16th is the last data set I had. These aren't all the images, but they're a selection of them. So you see what happened was it started off as just being an unresolved thing, the point source, and then something started to happen. Structure started to appear. And remember, that shape is effectively just a blob in the middle. So when you're seeing these big shapes, they're really just sort of blobs that have been spread out sideways. But we get these multiple structures appearing that are sort of moving on the sky, mainly sideways. Just if you want to just probably cut to the chase, we can measure the positions of these things. We can fit two-dimensional Gaussians. We can fit shapes to those positions, get the positions on the sky. And then from the positions, this is just a plot of how far they are, how far from the middle they are to the right and to the left. So east is to the left, and you look up at the sky, west is to the right. And so actually this is to the east, and this one is to the west. So these dots are telling you how far from the middle they are, and as a function of time. And I mean, I must admit, I was pretty surprised that these look like straight lines, because I just did this blindly. I just had these images and make the images. It's quite messy doing them, making the images, then fit these things. Just put the numbers you get from the fit into a plot, and it comes out pretty good actually in terms of an expanding system. So from that, you can, assuming you know the distance, which you think you have an idea of, look at what the expansion speed is. So roughly, one direction is about 3,000 meters per second. In the other direction, maybe 3,800. Some differences going on. Where does this cut through zero compared to this one? They're a bit different. I haven't done any real thorough analysis on this yet. And you've got to bear in mind that I'm only fitting two-dimensional Gaussians, whereas the real structure is probably a bit more complicated than that. So that almost certainly puts in some systematic errors in there as well. But this is quite interesting stuff. What next? We've just got some continued e-learning monitoring approved. because we're still seeing something, it's still expanding. We want to follow this, see what happens. We've got some imaging made with the European VLBI network. There's very large scale intercontinental stuff, which will be coming soon. We've got a colleague in Italy who's leading that. And the basic point is we're going to try and produce a consistent model of how this material is ejected and how it interacts with the material, the red giant wind, for example. And why is it sort of extended east-west? Is it actually sort of blown off the white dwarf just east-west, or is it somehow shaped by the environment? So loads of questions. I should probably stop there because you've got any questions. Thank you. Has anybody got any questions? Yeah.
Why is the radio or X-ray peak of the activity 10 to 15 days after the optical peak? Are they caused by different things? So if it was the explosion that causes the optical peak as well,
yeah,
they would be on top of each other.
Yeah, I think it's. I mean, that's obviously that's actually one of the questions we've got to try and answer. We don't understand that first rapid rise. The reason why normally that sort of thing happens is because you see, it's basically where the, you know, I don't know what your background is. You know about photospheres and things like that. No, it's just where, depending on what wavelength you're looking at, you're going to see. One is it could be brighter at one wavelength than another, so you might not even detect it in the radio because it's too faint initially, and then becomes brighter later. But also it depends on whether it's absorbed by the material outside it. So some wavelengths can be absorbed by the stuff outside, and some stuff isn't absorbed. So you can see the optical. Early on, what's happening is we think the optical photosphere expands, the sort of ejector expands, and you see this sudden brightening in just in the optical part of the spectrum. But as time goes by, it cools and you get emission at longer wavelengths, basically. But it's quite a complicated set of different physical effects that are all happening. But that's why you have to do these observations across all these different wavelengths, so you can then pin down make yourself a model of the actual underlying object, which then you can predict the emission from, and then you can compare it to the observation. Yeah. Anybody else? Yeah.
Do we have an idea of the length scale of the ejected material? Does the ejected material like feed back into some other processes, like astrophysical processes?
A length scale?
Yes, the length scale of the ejected material from the universe. Do you have an idea of that?
Yeah, yeah. I mean, you can just sort of get it from, even from this, from a graph like this would tell you that it was, this is 3,800 kilometers a second, 70 days. So you just multiply 70 by 24 by 3,600 by 3,800. That's how many kilometers it was. So yeah, you can get. We know the physical scale of all this structure, and we know one of the problems you've always got in interpreting these images is you don't. I've just measured these. This is very simple. I've just sort of measured the positions of these blobs. So I fitted the two-dimensional Gaussian to that, and in fact to that. It doesn't look like it's very fittable in this picture. You can see it on the get some. But the question is whether that gives you like a position in the middle there. That's what's plotted on those other graphs, right? But whether that represents, and then you can do the same thing for the time before. So you can do the same thing for that one, and all I'm plotting actually is the position of that one is one data point, the right-hand side one. And then the next one would be the right-hand side one there is another data point. So I've made an assumption that they're effectively the same thing moving out. That's why I was a bit, it actually looks like it produces this straight line. It really does look like it's the same thing moving out at constant speed. It might not be, it might be just where the radiation is coming from. Doesn't always the problem with astronomy. You see the emission, you see radiation from an object. It doesn't mean the object itself is moving. You could have like a whole bunch of gas in here, and then it could be that the point at which it's brightest is moving. It might not be the gas itself that's moving, right? and it would give you the impression of something moving along, but it could just be where the radiation's coming from. So that's, you know, a bit of a problem. But yeah, there's part of that acceleration going on, producing the non-thermal emission. There's this shock waves that produce the hot gas and thermal stuff. It's quite a messy old thing. We're hoping to get some Hubble Space Telescope pictures of it. I hope soon, because at some point it becomes resolvable with the Hubble Space Telescope. I should say the reason you can see this, if you look at the numbers on here, the numbers are only 0.05 arc seconds, is that? So this is a very sharp image compared to what you can see from the ground by visible light. So you'd have to go to something like the Hubble Space Telescope in space to get any chance of seeing anything like this sharpness of view. And the European Global Ice that we can get soon is even sharper. So that'll be interesting to compare to this data as well. Yeah.
Sorry. So, are there any other binary systems for which we have data?
Yeah. There's about these type of systems. There's about 10, 12 of them that do this that have this sort of behavior. There's one where we follow one every year that explodes every year. So rather than every 20 years, it explodes about every year. But it's in the Andromeda galaxy. So it's not even in this is in our galaxy. So it's somewhat closer. This other one that goes the most rapidly recurring is in Andromeda. So that's 2.5 million light years away, whereas this is only about 5,000 light years away. So you can't take pictures of that one like this. It would just be a dot. But it's interesting to study because it's a very extreme recurrence rate, means it probably is very close to exploding as a supernova. Yeah.
Yeah, it's kind of related. My question was going to be how rare are the recurrent novae?
Yeah.
But is RS off that special then, that it is so close that we can actually see what's going on? So it's the only way we have to get our models tested in a meaningful way.
Yeah, and that's why we're interested in it, because it explodes at a reasonably short time scale. But it's also reasonably close, so we can get good data on it. But remember that these things are at the extreme of a distribution of behavior, where we think the explosions recur in maybe every 1,000 years or every 10,000 years in many of the cases. So we know of a lot more novae in total. We know hundreds of novae, maybe 300-400 novae, of which maybe 10 or so have got recurrence on timescales of, observable timescales, human timescales. But that's interesting because that lets us sort of, try to understand.
Just a short follow-up.
Yeah.
Are these recurrences regular-ish?
No.
It's just a
Regular-ish, but that's one of the. So what are they? So 15 years ago. Before that it was 21 years, and before that it was 18 years. Before that it was 9 years. So there's sort of,
So you cannot be looking when something this important happens, and you can just
luckily there's the bright enough that the amateur astronomers who spend a lot of time looking at the sky rather than professional astronomers who spend a lot of time looking at computer screens. They're the ones that spot them. When we get something like the Rubin telescope, Large Synoptic Survey Telescope, as it used to be called, it's going to come on stream soon, and that will be amazing because that's going to do surveys of the whole sky that's visible to it every few nights. It'll take a few days to do the whole sky, and it's going to produce shed loads of data from variable stars of different types, transient sources. So there's going to be thousands of supernovae, for example, every night. So someone's going to have to work out to worry about all that data, and that's coming in the next few years. And it'll again revolutionize doing things like the visible light observations of the novae. Yeah. Okay, I better finish. So let's go and do some undergraduate interviews. Thank you. I hope that was sort of an insight. Apologies for not being able to answer all the questions yet.